It's like it's a really nice person. That's like, I don't know. It's fine. Ground black. No, that's like, let's go to
Page 7. Okay. So what I want to show today is that everything that we did with area, where we just did top minus bottom, we're still going to use that, but we're just going to take that and adapt it slightly to make it into a volume calculation. I think once we get past the concept of it, I think setting it up and it's going to feel pretty easy because we're just doing slide extension from what we did on Friday. So let's build the area first, and then I'll talk about how we're going to adapt from area. So let's recall finding the area under the curve y equals root x. So let's say this curve is y equals square root of x. Okay, between 0 and 4. So here's my shaded region. So if I want to find the area is just top graph minus bottom graph. The graph on top is the curve, and the graph below is the x-axis. So my area is just what we see in this formula here, top graph minus bottom. Integral from a to b. What are my bounds? 0 to 4, okay. And then the graph on top is the root x. The graph on the bottom is the 0. So we don't technically need that 0, but I just want to kind of show us that we are kind of following that formula. That root x minus 0 basically is representing the height component of our rectangle, and the dx represents the width component. So you can kind of see that width times height formula take its part within this integral, right? We're basically adding infinitely thin rectangle. We're adding up the areas of infinitely thin rectangles, right? So the height is obviously it's going to change. Root x minus 0 is going to be different, closer to 1 than it is closer to 3 or 4, but we just let it do all the adapting on its own. We plug in the formula, and then the rest of it, we just let it handle itself. So if we were to work this part out, I can just get this ready for power rule. So 2/3 times 4 to the 3/2 minus 2/3 0 to 3/2, I guess 16/3. We are getting an area calculation, so it's units squared. Right, so all that is familiar, right? We know how to do that. Even before this unit, we know how to find area. It's just that now we have to think about the bottom function, because that will help us make sure that this calculation comes out positive. So essentially, the integral notation allows us to add infinite numbers of differently sized rectangles to form this area calculation. Now with this method, we're going to take this same region created by f of x in the x-axis, but now we're going to take this two-dimensional region and we're going to rotate it 360 degrees around the axis. Okay. So we're going to take the same graph, okay, same shaded region, but now instead of just calculating the area, imagine taking this region and spinning it 360 degrees around the x-axis, which I'm going to call this axis of revolution. And the shape that's going to come out of it, we're not going to have to draw it, but the shape that's going to come out of it is going to be like this, this object that resembles a bowl, right? This circular bowl here, but it's not hollow. Okay, it is completely filled in. Okay, but you can also, we can think of it this way, where if we're adding infinitely thin rectangles to achieve the area of this region, we can also think of it as adding infinitely thin circular discs to create differently sized circular discs to create this shape. You guys see that? So we're still going to create this height between the graph and the x-axis. But now, instead of this representing the height of a rectangle, we're not going to let this represent the what of a circle, the radius, yeah. Radius of these circular discs, which I'm going to call big R of x. So let's just say that we're just examining one of these really infinitely thin rectangular discs. Okay, even though it's going to be infinitely thin, it's still going to have a face, a circular face. And we know that radius represents, call that R of x. And we know the area of that disk. What's the area of a circle? Pi r squared. So the area is going to be pi. We're going to call this representative radius big R of x squared. And we are going to give it that R of x designation because we know that, as the graph moves up and down, the radius of these infinitely thin disks are going to be changing, right? But not to adapt, we don't have to worry about the change. It'll just handle itself within the formula. Now, area is how many dimensions is area? Area, yeah, so area, right, area is 2, but then the infinitely thin component, this dx, is going to give it that third dimension. Okay? Just like how height is only one dimension, that dx gives it that width, gives that second dimension. But here, if we have the expression being area or pi r squared, if we add that dx, it'll give it that third dimension. So here's the volume formula for this. We call this a disk method, right? Because we're adding infinitely thin circular disks. So our volume is, I'll put this here and then we can adapt it. Our volume is integral from a to b, pi r of x squared dx. So you see that pi r squared, that's 2 dimensions. Dx is another dimension, so that gives it that third dimension. We're adding and accumulating these infinitely thin disks from one bound to the other. Now, typically that pi is not getting affected by the integral process, so we typically pull that pi out in front. So here's the adapted disk method formula that you see here. Usually the pi is out in front, and then big R of x. We'll just find R of x the same way that we found the height. We just do top minus bottom, and whatever expression that is, we just insert to the formula, and then we just make sure that the formula just takes care. As long as we set everything up, the formula and the calculator will handle everything else for us. Now, just like how we examined on Friday, if everything is from a left and right perspective, then if I have a horizontal radius, then everything is right minus left. If it's right minus left, then my expression has to be in terms of y, my balance has to be in terms of y, and all my equations will take on this form. It'll all look like x equals, okay? I'm not inserting the x equals into the equation, but whatever's to the right of the x equals is what is suitable for this equation. Just like how anything that I'm using for top minus bottom are all going to be functions, and all functions will have the form of y equals. So let me do some definitions here. We'll do this example again from scratch with the root x. Radius, r of x or r of y, is the distance from the axis of revolution to the boundary of the shaded region. That's going to be your top minus bottom expression. Okay, so now example 1, let's find the volume of the solid formed by rotating the curve y equals root x around the axis between 0 and 4. So we're going back to that y equals root x. But now we're going to actually find the volume of this particular object. Okay, so the first thing we want to do is make sure that we are rotating this around the x-axis. So as a reminder, where our axis of revolution is, we're going to be putting it here. Okay. I want us to keep reminding ourselves that this is not the edge of the diagram, right? This is really the center, right? This is the new center of the object, because everything is going to be rotating around that center. And that's how we can start at this axis and extend to the boundary, which will represent the radius of our circular region, right? So whenever you draw your radius, I like to always do this, start on the dotted line and then extend to the graph. I know it doesn't seem like a big deal right now, but when we introduce washer method and there's more than one radius, we want to make sure that we have our anchor. Our anchor is our axis of revolution. Okay, that's our center. So from the center, you're going to extend to the boundary. We call that radius, big R of x. So our radius is just how we would do top minus bottom with, imagine this is the height of a rectangle. We just do top minus bottom, but now we're going to call it R of x. All right, so root x minus 0, top minus bottom. Top is sitting on the curve. The bottom is sitting on the x-axis, which is just simply root x. Okay. Everything now, we can just insert into the formula here. My volume is pi, depth integral from where to where? 0 to 4. Big radius. 0, yeah. Root x minus 0, which is root x. I'm going to square that. That's nice because the root square root goes away. I'm just left with x, and this ends up giving us an easy integral problem here. Power rule. (16/2) is 8. Don't forget that we're just always going to have to attach pi to our answer. And this is volume, so units what? Units cubed. Okay, let's do another top minus bottom, and then we're going to explore what a right minus left can look like. It's always the right minus left that feels a little more challenging because we have to adjust our equation. Okay, page 8. Says find the volume of the solid created by y equals 2 minus x squared, revolving about the line y equals 1. So let's sketch that graph out a little bit here. So y equals 2 minus x squared, that's just a parabola that opens down with a y-intercept of 2. Same thing as y is equal to negative x squared plus 2. But the other boundary is y equals 1. So it's going to be over here. So really, I'm just dealing with that shaded region there. Okay, we're rotating this around the y equals 1. That's our axis of revolution. I'm going to abbreviate axis of revolution as AOR, axis of revolution. I'll put a dotted line there to indicate that is now my new center. I'm going to rotate that shaded region around that y equals 1. And basically, it's going to create an egg-shaped object, right? Again, we never have to worry about drawing the diagram. We just have to be able to pull the necessary information so that we can just insert into the formula. Okay, so we do this method. We know that there are no gaps within our object. So I'm going to draw a representative radius. And the integral will just handle all the other infinitely thin radius from one end to the other. Now, something else that we have to find is we got to make sure we can find the bounds. So how can I find those bounds algebraically? Yeah, set them equal, find the intersections, right? Okay. Okay. Integral from -1 to 1, top minus bottom. The top of my radius is sitting on the 2 minus x squared. The bottom of my radius is sitting on the 1, so I just subtract those two. Make sure, oh, I forgot to do this. I should have done this first here, my bad. Okay, let's get into the habit here. The radius, let's build the radius first. Radius is just 2 minus x squared minus 1, which is really 1 minus x squared. And once I have that radius, I'm going to insert into my this method formula. Pi, big radius squared. We can pull all this out, but let's just practice entering this in our calculator.
I don't have to like do power rule.
Right. Yeah, you're not gonna.
I can just calculate it.
Mhm. Now there are some FRQs out there that are non-calculator and you have to work it out by hand. But we can practice those as well. But even if it's non-calculator, for me, I'm still going to give you a calculator. You can still check your answer. I may ask you though to show your work for certain problems. Okay, so the way I like to do this, you can obviously put all this on your main on your integral formula. But when your expressions get messier and messier, it's nice to have your y1 hold your information, especially when we're dealing with what we're going to do washer method, where there's a gap and we got to have more than one radius involved. So I'm going to insert under y1. I'm going to insert my radius under y1, call it 1 minus x squared. Go back to my home screen. I'll do math 9. I'm going to leave pi out of my implementation. Okay. I'm going to just attach pi manually at the end, but I'm not going to get the calculator because I want to have that option of representing my answer as exact value. Once I insert pi, it's always going to give me a decimal value. So I'm going to go from -1 to 1. If I do var trace, I can select my y1. I'm going to square that. The nice thing about this method is less parentheses are needed because everything is stored elsewhere. Dx. Again, I'm purposely leaving pi out of my integral. And if I do math fraction, sometimes there's a chance that it'll give you a fractional value. Sometimes it can't, but if it can, that gives you an additional option there. So my volume is 16 over 15. Don't forget what? Pi. Units cubed. Okay, any questions there? All right, so we'll do top minus bottom. We'll do our intersection just like how we did our area. And then after we get our information that we need, then we can make a slight adjustment with that height component, call it a radius and square it. And also insert a pi to give it that third dimension. Okay, I want to show you what a disk method problem looks like if we're rotating around a vertical axis. Okay, let's revolve both of these about the y-axis. Okay, so it says given the region formed by the function, the x-axis, and the y-axis. So here is my shaded region, triangle. We're rotating about the y-axis. So my dotted line, my radius is going to be vertical. I like to do a little arrow, circular arrow to indicate I'm rotating. So it's going to kind of create this upside down or this cone with a vertex pointing up, right? So now our radius is always going to extend from our center. But this time, my radius is not going to be vertical, right? My radius is going to be horizontal. And because my radius is horizontal, just like how if your height or if your rectangle is horizontal, you know that your equation most likely will have to be adapted so that it can fit into the formula that we want to use. So we want to do right minus left, but the equation is not quite suitable for right minus left. We need to solve for a different variable here. So what would this equation look like if I solve for x? Sorry. Well, if I move that x over to the left side, x equals, is that what you said, 1 minus y? Okay. And then the left endpoint of my radius is sitting on the y-axis. The y-axis, that's an equation of what? X equals 0. X equals 0. So you see, I just want to show you that it's a good sign when you know that your equation is in that proper form of x equals. You know that whatever's on the right is ready for you to insert into the formula. Right. Our bounds is from the lowest to highest y value. What's the highest y value that you see? 1, right? And also in terms of y, right? We don't want to, if you use the x value, in this case, you won't make a mistake, but because they're the same value, but want to make sure that we're understanding we're stacking these infinitely thin disks from down here all the way to up here, right? This is the orientation that we're doing. Okay, let's build our radius. Right minus left, the right endpoint of my radius is sitting on the 1 minus y. The left endpoint of my radius is sitting on the 0. Okay, that's the hard part. The rest of it is just putting to the formula, right? So now v is equal to pi integral from lowest to highest y value from 0 to 1. Our big radius squared, quantity squared, dy. Now we can put it into our calculator. Again, we always use what variable in the calculator. Yeah, so even though on paper I want to see y, in the calculator you're going to use x. I got 0.333. If I do math fraction, math 1, gives me that decimal value, 1/3. Don't forget about the pi. Yeah, so if you do, if you hit math 1, convert to a fraction of it, or it'll try to. Sometimes if it can't, then you just leave your answer in decimal form and round to 3 places, and then attach pi at the end. Okay, let's try part B. Okay, we're rotating around, again, the y-axis. From your radius, you're going to extend to your boundary. A horizontal radius indicates, okay, my equation needs to be adjusted. They're not going to be in that easy form that we have. So we got to solve for x. I see plus or minus square root, but this is only going to be what? On the positive side, yeah. So we see the right endpoint is sitting on the curve. The left endpoint is obviously sitting on the y-axis, which is x equals 0. Just having these equations there gives me assurance that I know whatever's on the right is ready for my formula. Okay, my radius is right minus left. The right endpoint of my radius is sitting on the curve. The left endpoint is sitting on the y-axis. What's the lowest and highest y values here?
0.
0 to 4. Oops, sorry, b is equal to. We'll do root minus 4y in the calculator, then we can square it in when we do our integral notation.
Would be like a way to perform top to bottom on this, or like.
No, there isn't. Yeah, good question. The reason why we can't do top minus bottom is because our axis of revolution is this way. So we're forced to have to draw our radius this way.
Because like last lesson you can do the other way. Oh.
Yeah, last lesson we can do it the other way because it's area. But with volume, we're kind of forced into a box here because our axis is this way. We're having to do it this way. But I still want us to. The reason we did that exercise on Fridays, going back and forth is nice because if we realize we got to do right minus left, we know how to adjust accordingly. Okay, but yeah, that's a good point. We cannot go back and forth as easily, or probably a lot of times not at all with volume. But with areas, we have that potential flexibility to go back and forth. Okay, let's see if we can do page 9. Yeah, it's just the setup, right? I just want you to worry about the setup. Let me see here. Actually, I'll do part A with you on both of these, just so I want to help us make sure that we can get the intersections, and if there's logs involved that we can get those as well. So okay, I'll do this with us here. So page 9, number 1. Let the region R be the area enclosed by the function y equals 2x cubed. That's the cubic function that you see there with the curve. The horizontal line y equals 8 and the y-axis. Find the volume when we're rotating about the line y equals 8. So this one. Will this be a top minus bottom or right minus left? Yeah, because from the radius, we extend to the boundary, it's going to be a vertical radius. So top minus bottom will make it a little bit easier to set up. Now my bounds is going to be from 0 to whatever this intersection is, right? So the intersection I can find by setting the equations equal, right? This we can do by hand. Okay, I just drew a representative rectangle, sorry, representative radius here. The top of the radius is sitting at the 8. The bottom is sitting at the x cubed, the 2x cubed. And now it's easy, right? Make sure you don't forget to square your radius inside your integral notation. Looks like this is not going to be able to get me a nice decimal, nice fractional value. So just round to 3 decimal places and attach pi at the end. Yeah, I think we can get through A through D. Oh, sorry, all of page 9 together. So what's different about part B?
It's y-axis.
Which means that our radius is going to be what? Horizontal. Which means our equations has to be rewritten in a different form, right? And then our orientation for our bounds is different as well. In this case, what's going to be the lowest and highest, or what's going to be my bounds in terms of y values? 0 to 8. Yeah, we're stacking these infinitely thin circular disks from down here all the way to up here. And this is the true center of the object. We're not seeing the other half because the other half is getting rotated over. Okay, number 2. E to the x plus 2, that's the curve here, y equals 7, rotating about the line y equals 7. Top minus bottom radius, which makes it an easier problem. There's no need to rewrite our equation. Our intersection is just, you can graph the e to the x plus 2 and y equals 7 and look for the intersection by your graph, but we can also do this by hand. I can set these equal to each other and just solve for x. And take the natural log of both sides to bring that x down. So my boundary goes from the furthest left is 0, the furthest right is that intersection of natural log of 5. Top minus bottom. Top is sitting at the 7, the bottom is sitting at the e to the x plus 2. Now this one, let's really be careful here. We need a parentheses after our minus sign, otherwise we're not going to remember to distribute that negative through, right? So the rest is our calculator, sorry, dx. Okay, part B, rotating about the y-axis. Our radius is going to have to be flipped around. Our equations has to be rewritten in a different form. Oops, sorry. Let me get that e to the x isolated first. Here, I think we get look at the graph here and say, well, I know that this is the y-intercept of this curve. So if I replace the x with 0, I get 1 plus 2, which is 3. That can be that's my lower bound. My upper bound is 7, right? I'm going from 0 to 7. So I'm going to adjust the homework a little bit here. We haven't gone over washer method. We'll do the washer method for tomorrow, but I want to replace that with page 10. So from your homework pages, 5, 7, and 8, and then page 10 from the worksheet. So Page 12 has the key, so you guys can check your answers that way. And then the washer method, we'll extend that to tomorrow. Tomorrow, you guys will do the practice problems, AP, and then the washer method problems. I'll send out a reminder this afternoon, so you'll be clear as to what I'm gonna check tomorrow. Okay, come get your phones. Appreciate it. Okay, good, thank you.
You might be the whole last week.
Shirts, okay.
87.2. Okay, thank you. That's it. Yeah, right, so.
I don't know, sorry for the tree. We're standing when he's testing, like, sorry, that's the one. Yeah, that's not like, you're different in it, well, than doing. Yes, but, yes, first one states, I like this.